Well, hello, my name is Mikhail Golovny. I'm a senior developer and scientist at Salford Systems, and today I want to talk a little bit about the memory requirements for SPM and all of our data mining engines. For efficiency reasons, and that's something that I want you to understand, the entire learn sample must be loaded into memory. Now, the thing is, when CART or MODERS or 3Net or Random Forest or Rule Seeker, all of those engines, in order for them to run efficiently and quickly, they need to have direct access to all of the individual learn sample points available to the application. This imposes some natural limits on the amount of data that can be used during model building, or more specifically, according to our current internal assumptions, each data cell will occupy 4 bytes of memory. Now, in modern data collection systems and databases, etc., the data is usually stored in so-called double precision, when each data point occupies, say, 8 bytes of memory. Now, for most of our applications, that is not really required, because most of the internal routines like CART, MODERS, 3Net, they operate with sorted sequences of records. So therefore, about half of the memory can be saved by using a so-called single precision, which only occupies 4 bytes of memory. Now, what does it? What are the implications of this? The learn sample that has, say, 1,000 variables and 1 million observations will therefore have 1 billion data cells, jointly requiring roughly 4 gigabytes of continuous memory. So if you wanted to process a learn sample that has those specific dimensions, the total amount of memory that will be consumed by the learn sample inside of any of our data mining engines will have to be 4 gigabytes. Now, in addition to the data and the memory occupied by the learn sample, most of our engines also require an additional memory allocated to various indexing arrays. For example, when 3Net does its work, in addition to having the data itself, it also needs to construct indexing arrays that help processing all of the internal sort sequences and therefore make the application run very fast. Now, all of those indexing arrays, all of those extra, we call them work arrays, they also consume memory. And as a general rule, the memory consumption by the indexing arrays is somewhere equivalent and comparable in size to the memory consumed by the learn data itself. Therefore, we could say that the general rule as far as the memory requirements go would be the following. The total memory required by any of our engines is roughly 10 times the number of data cells, and that's basically the memory required in bytes. Now, the number of cells is naturally number of variables times the number of observations, and therefore if you have a learn sample, again going back to the original example of 1,000 variables and 1 million observations, that will jointly require roughly about 10 gigabytes of memory, out of which 4 gigabytes will be used by the data itself. Now, for some versions of the engines that coefficient could be, the multiplier could be reduced down to, say, 8, which is essentially just the 8 times the number of cells. For others, it could go up to 12, and it also depends on specific types of the model, the data configuration, and things like that. But that kind of gives you a fairly good generic estimate in terms of what to expect on the memory consumption when you access a specific amount of learned data. Now, what are the implications of this specific memory requirement? Well, it's presented on the next slide, and it has to do with the current existence of 2 different types of operating systems and computer architectures. The older ones are referenced as the 32-bit systems versus the newer ones, which is the 64-bit systems. Now, the 32-bit means that the 4 bytes internally are used to reference memory, and the 4 bytes usually means the 4 gigabytes of individual memory address spaces available to the application is general. But what it also means that technically, because there's some parts of memory needed by the operating system and so on and so forth, on a typical 32-bit memory architecture, the application will only be allowed to contiguously reference 2 gigabytes of memory. Now, that essentially restricts the amount of memory, the actual amount of memory that will be available on the 32-bit systems to be used for modeling. In particular, the maximum number of learn cells, according to the formula that I introduced on the previous slide, will be limited to roughly 200 million data cells available for learning. Now, notice that this is the limit that has nothing to do with the amount of physical RAM installed on your system. It is a hard limit imposed by the 32-bit operating system itself, and that's something that is basically unavoidable, regardless of how much memory you have, what kind of licensing you have, and so on and so forth. Now, the 200 million data cells is still a pretty large memory space, don't get me wrong. For example, you could have 100 variables and 2 million observations available for learning altogether, or you could reshape it in any other way. For instance, you could have it as a 1,000 variables and 200,000 observations, etc. But I also want you to realize that there is that limit imposed by the nature of the system itself, and if you want to go beyond that limit, if you want to process much larger data sets, then you would have to transition into the new style of memory architectures, and those are 64-bit systems that use an 8 bytes to reference any pointer in memory. Now, the 64-bit systems impose no practical limitations on the memory use or the memory available to be referenced by any application, including SPM, other than the physical amount of memory installed in the system, plus usually the paging file systems or swap file approaches that are dependent on the actual individual systems. Now, the bottom line, again, that if you want to work with learned data samples exceeding 200 million data cells, you basically have no choice but to start working with 64-bit systems. And that's the conclusion that we have here. Now, as far as the current development of SPM, we have officially released versions 6.6 and 6.8, and both of those versions only support 64-bit systems in the so-called non-GUI mode. Now, all of our software has the underlying philosophy that there is the command line application that can be compiled on any operating system, any platform. The command line application, which is also a non-GUI application, will support 64-bit operating systems, Unix, Linux, Windows, etc. But the GUI side of 6.6 and 6.8 currently operates only on the 32-bit platforms. The newer version of SPM, the SPM 7.0, which is about to be released, will fully support 64-bit systems in both GUI modes on Windows and non-GUI modes on Windows and all of the remaining available platforms. Therefore, as a transition, for those of you who want to have access to very large learned data samples exceeding 200 million data cells, give or take a little bit to that limit, will have to use 64-bit non-GUI versions of SPM. Now, the good news is that once you're using a non-GUI version, even if it's run on any other platform, any different systems, you can always save the output file as a GROW file or the output data sets, and then view those GROW files on a 32-bit Windows GUI application as if it were created there. And therefore, in the follow-up sessions to this video, I will introduce you to some important, powerful ways of dealing with the GUI applications and the non-GUI applications. As you will see, it is not that hard to teach yourself how to work in the non-GUI application because there is a large number of additional benefits that you will have access to. And then you can always view the end result in the GUI side, and that's essentially, in general, how all of these things work. Okay, so that's pretty much all I wanted to say on the memory use in SPM, and hopefully it will clarify some of the questions that you may have had up until now.